Hello. Welcome to today's Yebo Tutor live session. My name is James, and we are doing physics today. So in our physics session today, we'll be looking at electric circuits. We have an electric circuit from question number 8 showing on the screen. So this is where we are gonna start at. So we have looked at some questions on electric current. In the few weeks, we're looking at static electricity. So this specifically is a section on current electricity where the charges flow through a conducting material through in the circuit. So we have a circuit connected with a 12-volt supply and an internal resistance of 0.5 ohms, and parallel to it is a 2-ohm resistor and another unknown resistor R. There's a switch connected to the parallel part of the circuit where we have a 2-ohm resistor, and we have an ammeter, and this ammeter should measure the current through that point in the circuit. So this current, if you look at it, will be the sum of the current that will flow through the two branches of the parallel resistors. Then the voltmeter, you should know by now, the voltmeter doesn't draw any current. So it simply measures the difference in potential between the 2 points connected to it. So which means our voltmeter should measure the potential difference between the point to the left of the circuit, that is to the positive terminal of the 12-volt battery, and the negative, the other side, which is the negative terminal of the 12-volt battery. So take note, this 5 ohm is inside the battery. It's called internal resistance. So the terminals of the battery are taken from the points protruding from outside the dotted box. So this box represents the battery. Okay, so now let's look at what the question simply says. We have for this question, okay, the battery in the circuit diagram below has an EMF of 12 volts and an internal resistance of 0.5 ohms. Resistor R has an unknown resistance, so definitely should expect a question requiring you to find R at some point. So let's see how we'll get to that. So the first part is, what is the meaning of the following statement? The EMF of the battery is 12 volts. EMF. So what does EMF of the battery is 12 volts mean? So EMF means electromotive force. So that term EMF is electromotive force. And in this case, it is the amount of other forms of energy converted into electrical. So in this case, the other form of energy is the chemical in the battery. If you know how the battery works, it has got some electrolyte, which is the chemical energy that is converted through its interaction with the electrodes into an electrical energy, form. So we call that EMF. If we convert other forms to electrical, we obtain EMF. And when we convert, basically we talk of voltage when we are converting the electrical energy into other forms. So if we are working across the resistor, or we've got a heater or an electric bulb, then we convert electrical energy into other forms, and we simply refer to that as voltage. But now if an EMF is 12 volts, what does an EMF of 12 volts mean? So this should be let me see if I can show the screen. So we have an EMF equal to 12 volts. And by saying an EMF is 12 volts, this means that we are converting 12 joules of electrical energy per coulomb. The electrical energy that the battery supplies is a maximum of 12 joules per unit charge per coulomb. So the amount of energy obtained from the battery will be 12 joules per coulomb. So this is what 12 volts would mean. So 1 volt is equivalent to 1 joule per coulomb. So we can express this or explain this in terms of energy per unit charge. It is a supply of energy of 12 joules per coulomb, or the battery can do work of 12 volts of 12 joules per every unit of charge, or per every coulomb of charge. So that is what is implied by that statement. Okay, and the next part, the reading on the ammeter is 2 amps when switch S is open. So when we open switch S, like it is in the circuit, that's an open switch. So when it closes the contacts, then it's a closed switch. So when it's open like that, the current is the ammeter reading is 2 amps. Now the question is, what will be the reading on the voltmeter? What will be the reading on the voltmeter? So with we have a 12 volt battery with an internal resistance of 5 ohms. Then a voltmeter is connected across, and we have a resistor with a switch. The ammeter is there. Then there's another resistor of unknown resistance R, and I think this is 5 ohms. Let me check. It's 2 ohms. So this is 2 ohms. And this is 0.5 ohms inside, and the supply is 12 volts. Okay, so this is the circuit, and we're told that with the circuit in this condition, what will be the reading on the voltmeter? I think we are asked to give the reading on the voltmeter. So the voltmeter reading should be the potential difference across the battery, which is also equal to the potential difference across the resistor, the unknown resistor R. So what we have there is, we'll say the EMF, the supply, minus I times internal resistance minus I times unknown resistance is equal to 0. So this is conservation of energy. This is from conservation of energy. Where we're saying the supply from the EMF source is equal to the work done. So the energy from the EMF source is equal to the energy in doing work across the internal resistance, and the energy in doing work against the external resistance, the capital R. So which means if we add up all the energies, we get 0. That's why we're calling it a conservation of energy principle. So the EMF being 12 volts, 12 volts minus I, which is 2 amps times 0, 0.5 equals to IR. So in other words, we have said that this voltmeter is simply measuring the voltage across this resistor. Take note, all these points without any device connected between them. All these points to the left are basically the same potential. So point 1, 2, 3, 4, 5, 6, 7, 8. All those points and every point in between them are points of the same potential. They're just like one point. So they are connected together, they're shorted together, they have the same potential. So there's no work done in charges moving from this point back to the, or from the battery to those points. Then on the right side again, 1, 2, 3, 4, 5, 6, 7, 8 also constitute the same potential. So the points to the right and everything in between, the points along a conductor are in the same, have the same potential because we assume the conductor has negligible resistance. So that means this voltmeter is also measuring the voltage across, let me use a different color. So the voltmeter is ideally measuring the voltage across the resistor. So it's ideally measuring the voltage across the resistor, which is the product I times R. So now, which means 12 minus 1 is 11 volts equals to IR, and this is what the voltmeter reads. The voltmeter reads 11 volts. And what is the resistance of resistor R? So if IR is equal to 11 volts, then that means we can say 11 volts equals to 2 times R, and that means 5.5 ohms is equal to the resistance R. So this is from V equals to IR, the same thing that we have there. This is the same thing that we use here. So this was E minus VR minus VR equals to 0. Sum of all EMFs and potential differences in a closed loop is equal to 0. So this is what we call Kirchhoff's law. For those that would have come across it, that's the principle of conservation of energy applying there. So the potential drop or potential difference is given by current times resistance. That's from Ohm's law. So Ohm's law is also applied there, V equals to IR, which is this one. And we get our resistance to be, oh, I forgot about my screen. So we use V equals to IR from Ohm's law to express 11 volts equals to I times R, and I being 2, V being 11, we get I equals to 5.5 ohms. So that's how we get 5.5 ohms. So I was saying this formula that we used here is a derivation from Kirchhoff's law, which says the sum of all EMFs and potential differences in a closed loop. So this, our closed loop in this case, is this part of the circuit that makes up a closed loop. So E minus IR minus E minus I small r minus I big R equals to 0. So that's when we go in that direction around the loop. E minus IR minus I small r is equal to 0. That's a closed loop. Okay. So our next question says switch S is now closed. how does this change affect the reading on the voltmeter? Choose from increases, decreases, or remains the same, and explain your answer. So this is switch S, and when switch S is closed, okay, let me just clear that a bit. Okay, so when we close switch S, like that, when we close switch S, it means current now flows through the first branch and the second branch parallel to it through the 2 ohm resistor and the 5.5 ohm resistor. Don't forget this is 5.5 ohms because we calculated it through the initial condition when switch S was open. So now, how does this change affect the reading on the voltmeter? How does that change affect the reading on the voltmeter? Does it change? Does it remain the same? That is the potential difference across the same points. So how do we analyze that? This is a question based on analysis of the circuit. So there are a few things that you should take note of in this case. Excuse me. So we have, in this case, the 2 resistors parallel to each other, and we can calculate what their effective resistance is, and then use that resistance to find out how much voltage will be across the 2 parallel resistors. So these are like resistors in parallel. And so the 2 of them, we have a total resistance RT given by product over sum, which is a R resistor with 2 ohms times the resistor, which is 5.5 ohms, over the resistor of 2 ohms plus the resistor, which is 5.5 ohms. So this is product divided by sum. So this is the same as 1 over R1, the inverse of 1 over R1 plus 1 over R2. So we can use product over sum like this. That means R2 is 2 times 5.5 over 2 plus 5.5. And that's 11 over 7.5. The total resistance there of the 2 in parallel, you can calculate that. Tell us what you get. (11 over 7.5) is 1.47. ohms. So their effective resistance is 1.47 ohms. So if we have the same setup, in this case, 1.47 plus 0.5. So in other words, we know V equals to IR. And we have another resistance in series with this total resistance, which is 0.5. So which means effectively, the total resistance, including the internal resistance, will be RT plus the internal resistance, let's call it RI. So that's 1.47 plus 0.5, that gives us 1.97 ohms. And V being 12, I, we don't know. And R being 1.97. We get divide by 1.97. This gives us 6.09 amps equals to I. So why we want that current? It means the current flowing in this circuit, or which will be measured here, will be 6.09 amps. So this will measure 6.09 amps. And the 6.09 amps can be multiplied by RT, this resistance across the parallel circuit. (1.47) to find a voltage of 8.95. So that means if we so this is RT for the parallel circuit, for the parallel resistors, and this is the RT for the series, for the parallel combined with the internal resistance. So if we consider this 1.47, it is here. The 1.47, which one can I use? Purple is good. So the 1.47 is the total resistance here. That's the total resistance. This is like one resistor of 1.47 ohms. So with that one resistor of 1.47 ohms and a current of 6.09, it means the voltage across this part is what this voltmeter is now measuring. The voltage across that part. So this is now like a single resistor. We called it what? R parallel, like that. 1.47 ohms. So that voltage there is therefore I times R, which is 6.09 times 1.47. That gives us a voltage of 8.95. So the voltage increases. From that analysis, the voltage should increase. So the question, how does this change affect the reading on the voltmeter? Choose from increases, decreases, or remains the same, and then explain your answer. So this part of the working can be used as an explanation in support of why we say the voltage reading increases. The voltmeter reading increases. Did we say increase? What did we get? We got 8. It's actually decreases. Sorry. This is decreases because initially the voltmeter reading was 11 volts. Yeah. So that voltmeter reading decreases from 11 volts to 8.95 volts. So voltmeter reading, we say voltmeter reading decreases. It decreases. That's from 11 to 8.95. That's from 11 to 8.95. So it decreases. So the other way we can see that it decreases, you can just look at the circuit in terms of how resistances and voltages vary. Like initially we had only a 5.5 ohm resistor, which is this one I'm shading in red. So a 5.5 ohm resistor would have a greater voltage than a 1.47, or will require more energy, meaning a greater amount of voltage as compared to a 1.47 ohm resistance. So in introducing a 2 ohm resistor in across the 5.5 effectively decreases the resistance and also effectively decreases the voltage across those two parallel arms. So the voltmeter reading should decrease. Another way to look at it is in terms of current. Current was initially the two branches there would have to share current. So we can find how much current flows. The current which flows across the 5.5 will decrease. The current across the 5.5 will decrease. Am I right? Two into 8.9 is 4 something. Then 5.5 into 8.9 is 1 point something. Yeah. So the current across the 5.5 will decrease. And that across the 2 ohm resistor will be more. So you can see this from the parallel limb, the one across the 2 ohm, still also has a voltage of 8.95. So there's a voltage of 8.95 across those 2 points. The voltage across the resistor connected to a switch is still 8.95. It's the same as that across the 5.5. So we can find the current through each part. I equals to V over R, which is equals to 8.95, the voltage across the parallel arms, divided by the resistance 5.5. And this gives us 1.63 amps. So 1.63 amps is the current flowing through the 5.5 ohm resistor. Initially it was 2 amps, now it's 1.63. It has decreased. So when current decreases, it means the work done or the voltage across that resistor also decreases. The resistance is the same. V equals to IR, where is it? So when I decreases for the same R, V also decreases. So when voltage across this resistor decreases, the voltage on the voltmeter reading will decrease. So also that will show you that the more current always flows through the path of lesser resistance. So if you divide 8.95 by 2, you get 4. Something like 4.475, close to 4.48, right? Close to 4.48 is the current that will flow there across the 2 ohm resistor, and that is greater current than 1.63. So if you subtract 1.63 there, you've got 4.46. There you are. This one is giving us 4.46 amps. So that's the current across the 2 ohm resistor. It is greater than the current on the 5.5. More current always flows through a path of less resistance. So that's the analysis for this part of the circuit. That's the analysis for this part of the circuit. So if you'll be joining us, you are welcome, guys. We are here live. We are Yebo Tutor and here to help you. We have maths, physics, and chemistry running on this channel for you every single day or once in every week. So we have maths, physics, chemistry. The days are always given to you on our WhatsApp chat group. So if you don't have a link to that, you can drop a chat on the chat box of this channel. Then we can have you join our chat group and you can get notifications and other and other information pertaining to how we operate time and again on our channel. So we have announcements and everything else given from the channel. We also have a Facebook channel, which is Yebo Tutor NMU. You can also find us. We are present on that platform. So it is also for you to benefit. You should participate. We are a live tutoring platform where you can type your questions, you can comment, you can also call us via our Zoom platform by just scanning the QR code on the screen. Okay, so let's see if we can do one more question before we call it a day. We'll continue on more questions on electricity as we advance towards the electromagnetic induction section. So that part of the question is done. The next question is closely related. It's also in electricity, but it includes a graph. So I'm sure you guys also love graphs. By now, you should know that every question that involves a graph should be a very simple and interesting question. So this one says, learners perform an experiment to determine the EMF E and the internal resistance R of a battery using the circuit below. So you've got internal resistance showing and E on the dotted section of at the left of our circuit, which is basically the battery. And there is a variable resistor. That kind of electrical symbol shows it's a variable resistor, meaning you can vary its resistance. And we have current and a switch. So the learners use their recorded readings of current and resistance together with the equation R equals to EMF over current I minus R, small r, to obtain the graph below. So this is the graph that is obtained. So it's a graph of resistance versus 1 over current. So if you look at this circuit, you would basically vary the resistance, measure current, vary resistance, measure the current, vary the resistance and measure current. You get values of resistance and current. Your EMF and R are the same. So those are constants. Those are constants. So with the resistance values plotted on the y-axis and the recorded current values on the x-axis, according to that expression, it means, according to that expression, it would mean the gradient of this graph will tell us what the EMF of the battery is. It's a constant gradient, it's a uniform gradient, so it means we have a uniform source of current. The value is constant. The value of the EMF is constant. And we have the y-intercept. Is it the y-intercept is minus r? So the y-intercept is minus r. It is actually showing there minus r, which is the value of the internal resistance. So let's go on to see what the questions require of this part. What variable has to be kept constant in the experiment? So how would you answer that? Which variable should be kept constant in this experiment? So the EMF of the energy source or of the voltage source should be constant, and the meaning also its internal resistance or the same voltage source should be used. So it will have the same internal resistance, it will have the same EMF. So referring to the graph, write down the value of the internal resistance of the cell. So we need to find that y-intercept there, and give the value of R. So resistance there is in ohm. This is -5. This is 0. In between, we have 2 small squares representing 1 ohm. So that's 1. That's 1 there. That's 2 there. That's 3 there. 4 here and 5. And the intercept is at 3. So it means we would say from the reading, the y-intercept, the graph is of the form y equals to mx plus c, and our y, we have resistance equals to E over I minus R. So from this, we can say M is equal to E, because this is Y versus X, and this is R versus 1 over I. So it means Y is R, 1 over I is X, and M is E, C is equal to minus R. And in this case, C is minus 3 ohms equals to minus R, such that internal resistance R is 3 ohms. So our internal resistance is 3 ohms. Calculate the EMF of the battery. The EMF of the battery. So we'll go back to the circuit and find the gradient. So we need to choose points. We need to choose points in this case. We can choose points that are easy to read, like this point here. That point is at 10, that will be 10, 11, 12, 12.5. So we can say 12.5 minus the other point that we use for reference can be this one, the 0, the y equals to 0. So we said EMF equals to the gradient, and E equals to y2 minus y1 over x2 minus x1. y2, the top value for y is, we said, is 12.5. Let me confirm again. Yes, 11, 12, 12.5. 12.5 minus y1. y1, we're using the point along the x-axis, which is y equals to 0. And the corresponding point x2 is, again, 2 boxes represent 0.1 there. So that's at 2, 2.1, 2.2. So this point is 2 per amp. This is 2.1 per amp, 2.2 per amp at that point, 2.3, 2.4, and 2.5. So the end of the graph there is at 2.2 per amp. And we subtract, we say this is 0.1, 0.2, 0.3, 0.4. That will be 4, 5, 1 box closer to 0.5. So 425 in between. So that's 0.425. So you can calculate that also. You can calculate that. We said the EMF is equal to the gradient of the graph, which is given by change in y over change in x, or y2 minus y1 over x2 minus x1. So I have 12.5 there, divided by 2.2 minus 0.425. This is giving 0.7.04 volts. So this was in, this is in ohms, this is in per amps. So the unit there can be ohm amp, which is IR. This is IR. So this is 7.04 volts. So our EMF is 7.04 volts. I hope you guys are happy. I hope this makes a lot of sense. This should be making sense to you. So yeah, that's about it with this question. It was a simple and interesting question. Looking at the graph, and since it's a linear graph, you always know your linear graph is given by y equals to mx plus c. So it should be easy to analyze the y-intercept, the gradient, which is given by that, and y and x. So once you do that, you should be able to determine the values, internal resistance, and also the voltage. So that's it from me for today, guys. It was nice having you on the channel. See you again in the coming session. And from me and everyone else here at Yebo Tutor, we wish you the best with your exams. So don't forget to get in touch, like and subscribe our channel so that you get notifications each time we go live. Otherwise, all the best and take care. Bye-bye.